Hi class, I hope you all had a good weekend. So we're going to start talking about other worlds this week, not just about Earth. We've been talking about Earth to kind of motivate ourselves and help us understand what life is all about. But this week, we want to start looking outward and start thinking about how we might go about finding life elsewhere. So we're going to introduce a few concepts today to kind of help us start talking about other worlds. We're going to start with gravity. This first part of today's lecture will be kind of broad concepts about gravity. And then the second part, we'll talk about ways that you can use mathematically gravity to tell us something about the worlds that we're going to be thinking about. So in the background here behind me, this is Woolsthorpe Manor in England, in Lincolnshire. So this is the boyhood home of Isaac Newton, who is responsible for the universal law of gravitation, which is what we're going to talk about today. So this is the house that he grew up in. This is the house he retreated to during the Great Plague. He went home to live with his mother, and this is the famous apple tree that purportedly he inspired him to think about gravity. So we'll talk a little bit more about that. Okay, so let me go ahead and start a few slides. So gravity is really at the heart of everything that we talk about. When we start talking about other worlds, it is the dominant force that really drives things in the universe. And we'll talk about why that is in a little bit. Okay, so today we'll just start with some basic observations about gravity, things that kind of seem obvious, but as with all things, they aren't obvious unless you really think about them. We'll talk about what the universal law of gravitation says without actually mathematically writing it down. And then I'll show you a famous experiment that taught us a lot about gravity and demonstrate a lot of the principles of the universal law, something called the Cavendish experiment. Okay? So as we begin to start thinking about looking for life on other worlds, we're going to start bringing in some of the other sciences that we know about. We've been talking a lot about biology already. We've talked a little bit about chemistry already. Geology has certainly played a role. But when we start talking about looking at other worlds and trying to decide in all the vast universe what worlds we want to spend our time looking at, where are the best chances we're going to have of finding life, really the central science that plays a role here is physics. And we'll talk a little bit more about why that is. It has to do with energy inputs. It has a lot to do with the environments that the life forms might find themselves in. And so the two key things that we'll need from physics that we'll come back to over and over again for the rest of the quarter are gravity, which we're going to talk about today, and energy in particular. And we'll come back to energy sometime in the near future. Okay, so let's talk about a few of the things about gravity that we kind of take for granted. Unless you kind of sat down and thought about gravity and tried to enumerate all the things you know about gravity, you might not have thought about it before. Okay, so here I am when I was a little kid. My mom will tell you that she has no idea what I was doing. I have no idea what I'm doing, except I'm trying to break a hole in that ice that I'm standing on, which doesn't look very safe, but I'm still here, so apparently I survived. So the thing about gravity is always there. We've never been, most of us, I assume none of you are astronauts, most of us have never been in a situation where we have not experienced gravity influencing everything around us. It's the thing that's keeping me standing there on the rock and the ice that I'm standing on. It's the thing that's keeping the water there flowing downhill under the ice. And if I were to lift that stick up and drop it, it's the thing that would pull the stick down towards the ground. It's just kind of inherently obvious. And from the time you were the smallest kid to the time you're a kind of irresponsible kid like I am there, to you and I today, it's just there, and we know what to expect will happen in the world around us because gravity is always acting, right? It's what keeps your butt in your chair, what keeps your feet on the ground, keeps your coffee cup on the desk. It's what breaks your phone when you let go of it and it falls to the sidewalk, okay? Now, despite that kind of prevalence of gravity and that kind of wide-ranging influence that it has on everything we see around us, there's a curious fact about gravity that physicists will tell you, okay? And that is gravity is the weakest force in nature. Now, what do we mean by that when we say that? There are four fundamental forces in nature, which you may have learned. There's gravity, there's the electromagnetic force, there's something called the nuclear force or the weak nuclear force, and there's something called the color force or the strong nuclear force. And what we mean when we say that gravity is the weakest force, we mean if we compare the strength of gravity to the strength of the strong nuclear force, those two are different by about a factor of 10 to the 42. Okay, or gravity is 10 to the minus 42 times weaker than the strength of the strong nuclear force. So it's the weakest force in nature. Okay, all the other forces are extremely important. Okay, but you already know that gravity is extremely weak. And the reason you know gravity is extremely weak is because if you go to your kitchen right now and you get an apple out of the fruit basket and you try and pull it apart with your hands, you most likely will not succeed. And that's because all of the intermolecular forces that are holding that apple together are stronger than the force of you trying to pull the apple into two halves. By a similar token, if you stand up in your chair right now, you can, using a little bit of chemical energy from the Dr. Pepper you drank right before you watched this lecture, you can jump up in the air. You can overcome the entire gravitational pull of the Earth using just a little bit of chemical energy stored in your muscles from the meal you ate a while ago. Gravity is extraordinarily weak. Otherwise, you would not be able to jump off the surface of the Earth. Okay? It's so weak, even Dairy Queen can keep ice cream in a cup when you turn the cup upside down. I don't know about all of you, I'm desperately wishing for some Dairy Queen blizzards right now. So cherry blizzard is the way to go all the way, okay? So gravity is the weakest force in nature, but when you look at all of the forces, it's the only force that acts over huge distances. And so even though it's the weakest force, it is the most important force in astronomy. Nuclear forces only happen on the scale of atoms. Electromagnetic forces only happen on the scales where charges can see each other. Over long distances, everything's charge neutral, okay? Gravity is the only force that acts on enormous distances, and so it's the most important force in astronomy, okay? Unless you're talking about the force, and we'll come back to that some other day. Okay, so what we use to describe gravity in the universe today is called the universal law of gravitation. It was first written down by Isaac Newton in his famous book called the Principia in 1687. Those of you who know a little bit of science history will know there's a lot more in the Principia than just the universal law of gravitation. In particular, the fundamental laws of motion. For every action, there's an equal opposite reaction. All that stuff is in there. And also Newton's first description of the calculus is in there. Okay, but we're going to focus on the universal law. And the universal law has a few basic properties that mathematically we'll come back to in the next part of the lecture. So first of all, it's an attraction between all masses. All masses exert gravitational force on all other masses. Okay, now this famously is the observation that Newton made or was inspired to make when he was near the apple tree on his mother's farm. This is usually depicted as is shown in this picture here with the apple falling on Newton's head, but he observed an apple to fall to the ground from the tree and asked, why did the apple fall towards the earth? He then reasoned, or he was inspired to think that the same force that pulls the apple towards the earth is the same force that keeps the moon in orbit around the earth, okay? And you can see the moon there in this depiction. So those two things were intimately connected in Newton's mind. And we, if any of you want to talk about it, we can go into that by a lot more detail. But all you need to know is that it's an attractive force between all masses, no matter what they are, okay? It is always attractive. It's unusual in that way. There is no repulsive gravity. The strength of gravity that you feel depends on the size of the masses involved. So bigger masses produce stronger gravity. And the strength of gravity you feel depends on the separations between the masses. So the apple feels a very strong gravitational force because it's very close to the Earth. But if I put it 5 trillion light years away from the Earth, it won't feel very much gravitational attraction to the Earth at all. Okay? So those are the fundamental tenets of the universal law. And when we write it down mathematically, those are the four things I want you to remember. They're the four things that you should be able to see acting when we write down numbers and use the universal law to make a few calculations about the worlds that we're going to be looking for life on. Okay? Now, the thing that was probably the most inspired thought that Newton had here was that gravity is an attraction between all masses, right? He could have just as easily thought that there was nothing the apple had to do with gravity. It was all the action of the Earth. But what he actually said was, if the Earth is pulling on the apple's pulling on the Earth. And more to the point, what he actually said is, he's pulling on the apple and the apple's pulling on him, whether the Earth is there or not. Okay, and that's an extraordinary thought, because at that time, and still today, this is very hard to measure, but at that time, no one had done any experiment at all that suggested an apple sitting on your desk is attracted to you sitting on the other side of the desk, right? There was no experimental evidence, no experimental result that would have inspired you to make that thought, but that was Newton's great insight. Okay, so it was actually proved very quickly thereafter that that was in fact true, and it was proved in an experiment that you can do in your own basement if you are so inclined. So that experiment's called the Cavendish experiment. So the reason in this situation you don't notice the apple being attracted to you is because the Earth is so much larger, then the Earth pulls on the apple so much more strongly, and so it dominates that interaction. Any small force that you exert on the apple doesn't really deflect it in its fall towards the ground at all. Okay, so what Cavendish's great brilliance was is he said, well, we got to get the Earth out of this problem. And since in the 1700s when he did this experiment, they didn't have rocket ships, he had to do this on Earth somehow. And so the way he did that was he put everything on these platforms. Okay, so these platforms basically took the Earth out of the problem because nothing's moving up and down. They're on these platforms, so they can only move side to side. Okay, and one of them, as you can see, is tied to a long thread. And so if those move side to side, what the thread does is it twists and allows them to move side to side freely, but since they can't move up and down, the Earth is removed from the problem there, okay? So this is called a torsion pendulum. That twisting around the thread is the torsion pendulum bit of this, and then the two big masses are sitting there. So what Cavendish basically did was he put two masses on a thread like this, he made a torsion pendulum, and then he set two big masses on the ground right next to it, and that pendulum twisted till the masses touched each other. And they picked up the masses and he moved them, and the thread twisted back until the masses touched each other again, okay? So this is the proof that the little masses on the end of the torsion are attracted to the big masses that he was setting on the ground there nearby, okay? So, as I said, you can set this up, this experiment on your own, and I did that, okay? So here is my experimental setup. You see the big block of styrofoam there. That's basically the platform that I put two of the masses on. I have four masses there. They're little jugs full of BBs. I got my torsion thread and everything there. Okay, so this is a video of the experiment I set up. So the torsion pendulum you can see is hanging straight down. So I have a webcam looking straight down the torsion fiber. Okay, so the bar that you see that's diagonally from the lower left to the upper right, that's the torsion pendulum. And then I have underneath it two boards where the BBs, the stationary masses, are sitting. Okay, and so this is a time-lapse video. It took about 2 days for this to happen, okay? But if you watch, I'm gonna play it, and over the course of 2 days, that pendulum twists and the masses attract each other, okay? So I'll start that video. Okay, so you see a lot of bouncing there initially. So the gravitational attraction is pulling the masses together, but the pendulum doesn't want to, the thread doesn't want to be twisted. So it tries to untwist itself. And since the forces we're talking about are extremely tiny, it can basically overcome that. But over time, the gravitational attraction of the big masses overcomes everything, and it pins the masses against each other. Okay, so you can see it's all enclosed in a big cardboard box there. So this was completely closed off, so there were no air currents or anything because the air currents were enough to overcome the very tiny gravitational forces that we see going on there. So, okay, so that is the Cavendish experiment. It shows that all masses absolutely are attracted to each other. So you sitting there on your desk, you're attracted to your laptop's attracted to you, you're attracted to your coffee cup's attracted to you. It happens, okay? But on large scales, the biggest masses are the ones that dominate. So that's why you and I are attracted to the Earth, and we don't notice that we're attracted to the iPad sitting on our table. Okay, so we'll talk a little bit about the gravitational scale, gravity in the next part of the lecture. We'll talk about how to compute how big and how strong it is, and then we're going to use that when we talk about other worlds. Okay, so I hope you're all having a great day. I'll talk to you soon.